Our last lab is acid-base titration. So what we're going to do is use a known concentration sodium hydroxide solution to analyze an unknown acid. In this case, officially our acid is acetic acid, which is a component of vinegar, typically around 5%. And the way this works is that we add something called a chemical indicator, and that chemical indicator changes color depending on what the environment it's in is. So in an acidic environment, phenolphthalein is colorless. In a basic environment, phenolphthalein turns a light pink. The reaction is that we're taking acetic acid, we'll just say that's our H+, we're adding sodium hydroxide to it, and that produces water. We have a fixed amount of the acetic acid that we start with. It's a 5 mils of the solution, and then we just add incrementally sodium hydroxide solution until we reach the point where the number of moles of the two are equal. And what happens then is we go from a region of excess H+, that's where we start, to excess hydroxide. So as soon as we see the color change, that tells us the volume of sodium hydroxide that was needed. And what we do is we measure the volume and we see the color change and we record that information and use its volume and concentration to figure the number of moles, which tells us the number of moles of acetic acid that we must have had in that original solution. Okay, very common technique, acid-base titration. All right, let's look at the data. So we've got the burette loaded up with sodium hydroxide, and now we need to read the initial volume and do the titration. So we want to try to read this to the 100th of a mil. So looking at that, looks like about 0.3, maybe 0.29. Let's call it 0.29. As we do the titration, we're putting the base, which is in the burette, into the receiving container, which is our 100 ml beaker. The beaker, of course, contains the acetic acid. So as we let the base go in, we saw that there was a brief pink color as we locally had an excess of hydroxide. That gets consumed by the acid as the titration goes, and so the color doesn't last. And we want to keep doing this titration until we get a permanent, persistent pink color. It takes longer and longer for the pink color to disappear. And we keep adding base until we see that pink color stay persistent. And ultimately we have a pink color that is persistent. So at this point we've reached the end point. We have to be careful that we don't overshoot it. And now we need to see what the actual volume was. So here's our endpoint for trial 1. We want to read that guy as close as we can. And I'd call that one 45.35. 45.35. So from our observations, we determined the initial and final volumes of the sodium hydroxide in the burette. In trial 1, I read that as 0.29 and 45.35. If your eyes are sharper and you want to use your own numbers, that's fine too. Okay, and then from just the videos, you need to figure out what your initial trials were for trial 2, trial 3, initial and final volumes. All right, then for all three of these, we care how much we actually used. It really doesn't matter what our initial or final were. Rather, we care how much was actually delivered, how much sodium hydroxide was delivered to the receiving flask containing the acid. So we do some quick subtraction here, and I see that in trial 1, I used 45.06 ml. And then again, you're going to have to work those guys out. We can do an average. Hopefully these numbers are fairly close to each other. If they are, then we did the experiment well. If they're not, then we need a little practice. For future calculations, we're just going to convert our mils to liters. So straightforward, I suppose we ought to show that as a roadmap. Mils going to liters, but obviously that'll be divided by 1,000, so about 0.045 liters. All right, pressing on, we want to figure out how many moles we have. So we know the concentration of the sodium hydroxide, and we need to know the volume that we used. All right, so for trial 2, let's get a good reading here. You guys make the call on that. So this will be written down as your trial 2 initial volume. Here's our final volume for trial 2. So give that guy a good read. And finally, here's our third trial, initial volume for trial 3. Go ahead and take that reading, write it down for the third trial. And last one, the final volume for trial 3. Get that guy a good read. So we need to go from our liters of solution to moles of solution, or rather moles of NaOH. And to do that, we have that the concentration of the sodium hydroxide, I just sneak that in just now, 0.1012 molar, which is of course moles per liter. So we'll do that liter to mole conversion and come up with a number of moles. To go from moles of sodium hydroxide to moles of acetic acid, we know that the stoichiometry of this was that for every, I'll just write this as HA for acetic acid. And the important part is that it's 1-to-1. So what we need to do here is really a mole to mole conversion. That is going from moles of sodium hydroxide that we just calculated in A7 to moles of acetic acid in A8. It will be the same number, but I want to see that you've done that mole to mole conversion. All right, molarity of the acetic acid. What's our definition of molarity? So molarity of the acetic acid is moles of the acetic acid over liters of the solution, which is our vinegar. And remember, we used 5 mils of vinegar there, so we want to convert that to liters. Okay, anyway, just based on the ratios that we used, where we used about 45 mils of sodium hydroxide for 5 mils of the vinegar, that tells us we should have about a 10-to-1. I think it's going to be a 9-to-1 increase in concentration. So I'd expect to see a molarity of our vinegar of around 0.9 or 1 molar. All right, the grams. This is going to go from either mils or liters, but mils of the vinegar solution to liters of vinegar, and since we've now calculated the molarity, we can go to moles of vinegar, or sorry, moles of acetic acid, and then we have to look up the molar mass and come up with grams of acetic acid. Okay, and so that's grams of acetic acid, not grams of vinegar, acetic acid being just the 5% or so of the total solution. All right, and then here, I'll just leave this one to you, but we need to write out what a mass volume percent means, and recognize this is going to be mass of the acetic acid calculated in A10 divided by the milliliters of the vinegar solution that we used. And of course, that's a fixed volume. It's 5 mils for everybody. And we expect this to be somewhere in the neighborhood of 5%. All right, so quick calculations on this. They're pretty much what we need to do for the solution chapter in chapter 9, but we've applied that to acid-base chemistry. And then the last two questions here, great questions. The things that we absolutely must do here is write out chemical reactions. So it's a good practice here to do that. So our reaction involving HCl and magnesium hydroxide. I'll give you a little hint here. The fact that there's two hydroxides should be reflected in the stoichiometry of what's going on there. One of your products here, of course, will be MgCl2. In the second question, we've got a similar thing going on. We've got our sodium hydroxide reacting now with a triprotic acid, so the balanced reaction should reflect that. All right, here we're starting with mils of the stomach acid of our HCl, so mils of HCl, and we need to ultimately get to grams of sodium hydroxide. So we should see a roadmap that reflects that, and then a calculation that does the same. And in question 2, we're going from mils of phosphoric acid to mils of sodium hydroxide. So again, our roadmap should include those concentration terms and the balanced reaction stoichiometry, though we don't have any molar mass things to worry about here. There's no grams involved. To wrap this up, how about we just turn in the pre-lab questions, which is page 173, and the part A calculations, which is this page, page 174, but we don't do part B. So just turn in those 2 pages, and we'll call it a day.